So we're moving to active sensing. And this is a tradition in the GRASP lab in the University of Pennsylvania. And Kostas Daniilidis was director of the GRASP lab, and he will present us latest on this. Thank you, Kostas.
Thank you very much. My talk is about perception with active sensing, event sensing, and symmetry. It could be called also how to survive in the age of GPT if you received your PhD in 1992. So when I was doing my PhD, at least at the beginning, there was only one video sequence available. One video sequence with 22 frames. Compare it with the millions of YouTube clips that we have now to process in order to achieve actually state-of-the-art in video understanding. And in 1981, my advisor, Hans-Hermann Nagel, published an article in August of 1981, the same time, the same month actually, that Takeo published the legendary KL features and tracking at Ichikai. As a matter of fact, Takeo says that the method was so simple that they were embarrassed to send it to a vision conference, and they sent it to Ichikai conference where no vision people would be, so that they would not be embarrassed. And using these 22 frames of the taxi sequence, in 1981, they were looking closely at pixels. And this is what I really learned during my PhD. When something does not work, this was always Friday night when I was meeting my PhD advisor, I really had to go to the pixels themselves and explain at each pixel, something that now in deep learning you call attribution or interpretability. You have to explain at each pixel actually what happens. And the values that you see at these pixels, the third value in particular is the Gaussian curvature, and this is how these years you would define corners and build tracking, and then also three-dimensional models. This was 40 years ago. We improved it 10 years after in 1992. But fast forward, in 2020, the state-of-the-art in optical flow first requires training. It cannot be computed by a formula like KLT or what I did during my thesis. And it needs ground truth optical flow. The notion of ground truth was really unknown to us. I mean, it was known only to evaluate, not to use in training. And it uses 100,000 iterations on the FlyThings 3D, Kitty 2015, Sintel, HD1K, MassFlowNet, and PWCNet++ in order to be trained, plus a fine-tuning of another 100,000 iterations on the Kitty 2015. And this uses 5.3 million parameters. Admittedly, the produced optical flow is amazing. In 2019, Rich Sutton talked about the bitter lesson. The bitter lesson is that even if we want to inject geometry and physics and any math we have learned in the neural network, at the end, just scaling the number of data and the number of GPUs will produce a better result. And thank God the roboticist replied to this and actually also noticed, Rod Brooks, that even the way we build the neural networks, for example, convolutional neural networks, is designed by using human knowledge, the idea of invariance in translation, and that's why we can make them efficient. And it would be really pedantic to the extreme to really leave everything just to scaling data and compute. And I have found this in Reddit. It is a picture of how to try to really balance two spoons at the edge of a glass, and I compare it to achieving exactly the same task by duct tape. And while both of them actually have human knowledge and physics, you learn much more, and also you learn actually what we call the minimal case many times in geometric problems in the left case. And it seems that nature follows a lot, actually, of the left. So the fruit fly consumes just 10 microwatt total of energy, one of them going in computer vision, and yet can achieve amazing tasks that we cannot yet achieve in this size with any quadrotors using 60,000 neurons. So the first lesson to achieve this is really to rethink sensors, to have sensors that are fast, low power, and low bandwidth. And my colleague Vijay Balasubramanian at the University of Pennsylvania, they have done a study by extrapolating from the number of ganglion cells in the guinea pig, and the actual bandwidth that comes out of the human eye is 8.75 megabits per second, compared to the high-definition bandwidth that we use nowadays in cameras, which is 1.32 gigabits. So the eye already does a Netflix-like compression before it enters your brain. And if you go to the actual calculus of light, everything we use today is a CMOS camera, so pretty much, or CCD, where we integrate just the light over an integral. This has been done for photography and video, not really for robotics, while we could have counted the photons separately, what is happening in what is called SPAD sensors, or even counted the differences and producing asynchronous only events. And in event sensing, and Davide Scaramuza yesterday showed much more impressive examples than what I will show. He is really the pioneer on that. In event sensing, we have a much lower bandwidth. We can have a high dynamic range, and we don't have motion blur. And most important, we can really use it in battery-powered devices. And you can see here in the upper, this is one of our optical flow computation of the very fast fidget spinner. You can see that it can compute under extremely fast motion and in very dark conditions. So this is the actual gray value on the left, and we cover the light. And the optical flow computation is not affected by the covering of the light at all. On the bottom, we have one of the classic sequences where we compute optical flow with events. Moreover, we show here that even if you had a slow-mo sensor with 240 frames per second, the integration of photons still produces so much motion blur you cannot differentiate the actual particles of water. And this is the optical flow on the left from a 240 frames per second iPhone image sequence, and this is the event flow where you can really see the whole turbulence of water. In addition, if we have if we can apply structured light, we can really synchronize the actual structured light with events at a very high frequency. And we can then isolate the events with filtering that are projected from a diffractive projector in this case, and obtain 1 kilohertz depth, which we show on the right encoded with color, and on the left we show the actual events. So this lesson number one is that we don't have to use RGB frames. We should continue using them, but we can add other sensors. And of course, you can add even more, actually, other senses. I will show examples later, and you heard from Catherine and Alison Domenico in this morning. Second lesson is that brains are built based on the principle of symmetry. So after signals leave the visual cortex, they go to different pathways. One is the where pathway, which really means that it preserves equivariance, and the other is the what pathway, which is what preserves invariance. And optical techniques now that with which you can really study the brain has shown that there is an actual area in the fly. This is the ellipsoidal area that you show over there, which is really equivariant to the heading perception of the fly. So, and you see that when the pattern rotates to the right, the activation in this area rotates as well. So the brain of the fly with so few neurons still encodes beautifully symmetry. And this is what we try over several years to model with equivariance. An equivariant map is a map, feature map in a neural network that computes with a transformation. In this case, here is the SO3 rotation transformation. And we have done this even for three-dimensional objects by building SO3 equivariant features of the sphere, which really transform the same way, equivariant way, like in the WHERE pathway in the brain. And then you can integrate them and produce an invariant representation like the WHAT pathway. My third message is back in what Ruzena Badji pioneered in my lab with active perception, including others. In active perception, we just don't take videos from YouTube. We really explore the actual scene. We sample the scene. And as Gibson said, no one is aware of the sequence of the sampling. One is aware always only of the total scene. And we applied this in the most modern representation of scenes, the radiance fields, using 3D Gaussians. In this representation, by using the Fisher information matrix with respect to the unknowns of the 3D Gaussians, you see here an encoding of the Fisher information by color. And this is the actual information that every view is encoding, and we select the view with the best actually information. In collaboration with Monroe Kennedy, who is building amazing haptic sensors at Stanford, we have extended it to not be just the next best view, but the next best sense. And here in a quite challenging scene with 3D printing of the Stanford rabbit, we show the difference between using the Fisher information to choose the next best view and later the next best touch versus the random views on the right. Now, what about AI though? Or what they call generative AI, or what we call foundation models. On the left is my lame attempt to use GPT to produce a slide. And so we can very creatively incorporate what we call foundation models in geometric problems. And the way we do that is that we have an equivariant encoding, position encoding for every ray. And then imagine that every ray, instead of having just RGB, having segmentation features like DynaV2, having a depth prediction from Zoe depth or depth anything, or even having a feature that supports tracking like the co-tracker. And I want to close with this sequence, going back 40 years after the optical flow I showed with the Hamburg taxi sequence. This is by producing dense tracking. Pixels of same color are the tracked ones. They keep the same color in the same position, and show how we can actually use these foundation models, not in an end-to-end model. We still use geometry here, but just enhancing the RGB with all these features from recent AI models. And I close with three not bitter, but really sweet lessons that it's definitely worth working on new sensors, and event-based cameras have proved that. Incorporate as much geometry, as much symmetry as you can in order to produce smaller models. And if you do robotics and not just use videos from the internet, have your robot actively explore the environment. Thank you very much.
Thank you, Kostas. Question?
Actually, not so much of a question, more of a statement. Rich, I've asked him actually about this bitter lesson because it annoyed me just as much as it annoyed probably anybody in this room. And he actually told me I should read not only the first part of the bitter lesson, but also the second part, where he basically states that we should create systems which actually discover these inductive biases like the symmetries you just mentioned in the last slide automatically and try to come up with more automatic processes to bring more of these inductive biases into life. So he didn't mean only the first part, which we have taken a little bit too personal in our community.
Indeed, we have taken it very personally. Actually, every morning that you wake up and read the archive, you take it personally by what you read. And but even the discovery, yes, we have done work on discovering symmetries. The problem is that you still need, I mean, this is more like an evolution process, right? It's not something that happens during child development. The discovery of the symmetries and their encoding in the brain happened during evolution. And this is indeed a very good second way to encode actually inductive biases by not writing the actual formula of SO3, but by having your system actually discover it. And there are examples about it in MNIST, the number 6 versus number 9. The brain knows exactly not to apply equivariance there to differentiate the two.
Thank you. Is there a quick question? I see.
Hey, nice talk. And my question goes more into what you're actually doing. And I wanted to know, when you're designing a system, how do you define where the middle point is? To what extent would you define inductive biases yourself, opposed to having a system learn it?
Yes. So I must say that before the foundation models, we really were all about inductive biasing, trying to also use as much self-supervision also as possible without using ground truth to induce the biases in the weights. Now with foundation models, if we have a compact, like a tiny model, at least during inference. And this is a big difference between what you use during testing and during training and what you use during inference. In particular, in event processing and spiking neural networks, you can have really surrogate networks for training and then use something that is an approximation of the network you trained. Something like that we try also to do now with symmetry. So you try to use really something that approximates symmetry during inference is much more actually efficient, because at the end, in robotics, we want to have both energy efficient and something that runs in real time. And sometimes the explicit actually introduction of symmetry is a lot of memory consuming and has other problems as well.
Thank you very much.